Imagine a place where gravity is so strong that nothing, not even light, can escape its grasp. This is a realm where the very fabric of reality is twisted and contorted in ways that defy our everyday understanding. This is a black hole, a celestial object so dense that it warps the fabric of space-time. The concept of a black hole was first theorized by John Michel in 1783, but it wasn't until Einstein's theory of general relativity that we began to understand their true nature. Black holes are born from the remnants of massive stars that have exhausted their fuel and collapsed under their own gravity. When a star reaches the end of its life cycle, it can no longer support itself against the force of gravity, leading to a dramatic implosion. These cosmic abysses are regions of extreme density and gravitational pull, where the laws of physics as we know them break down. The core of the star compresses into an incredibly small volume, creating a singularity where density becomes infinite and the known laws of physics cease to apply. Their very existence challenges our understanding of the universe and raises profound questions about the nature of space, time, and gravity. Black holes are not just theoretical constructs, they are real entities that we can observe indirectly through their interactions with surrounding matter. Black holes are not empty spaces, they are filled with a tremendous amount of matter compressed into an incredibly small volume. This matter forms an accretion disk around the black hole, where it heats up and emits X-rays that we can detect with telescopes. This creates a gravitational pull so powerful that it creates a region of space-time from which nothing can return. This boundary is known as the event horizon, beyond which escape is impossible. The event horizon is not a physical surface but a point of no return. Their invisibility adds to their mystique as they cannot be directly observed. Instead, we infer their presence by observing the behavior of nearby stars and gas clouds, which are influenced by the black hole's immense gravitational pull. We can only detect their presence through their effects on surrounding matter and the bending of light around them. This phenomenon, known as gravitational lensing, allows us to map the presence of black holes even though they themselves emit no light. Black holes are not cosmic vacuum cleaners. They do not suck in everything around them. Objects must come very close to be captured by their gravity. Most stars and planets in a galaxy will orbit a black hole without ever being in danger of falling in. Only objects that cross the event horizon, the point of no return, are inevitably drawn inward. Once an object crosses this threshold, it is lost to the black hole forever, adding to its mass and further increasing its gravitational pull. Black holes continue to fascinate and challenge scientists, pushing the boundaries of our knowledge and inspiring us to explore the deepest mysteries of the cosmos. They are laboratories for testing the limits of our physical theories and understanding the fundamental nature of reality itself. The event horizon is a crucial concept in understanding black holes. It is the boundary around a black hole beyond which escape from its gravitational pull is impossible. Imagine a waterfall. Once water goes over the edge, it cannot climb back up. Similarly, anything that crosses the event horizon of a black hole is destined to fall towards the singularity at its center. The event horizon is not a physical barrier. It is simply a point in space where the curvature of space-time caused by the black hole's gravity becomes so extreme that all paths lead inwards. Even light, which travels at the fastest speed possible, cannot escape the pull once it crosses the event horizon. The size of the event horizon is directly proportional to the mass of the black hole. A more massive black hole has a larger event horizon. The event horizon is a key feature that defines a black hole and distinguishes it from other celestial objects. Black holes are invisible to telescopes that detect visible light, X-rays, or other forms of electromagnetic radiation. These enigmatic objects, with their immense gravitational pull, do not emit any light that we can see with our eyes, or even with the most advanced optical instruments. They are in essence the ultimate cosmic hide-and-seek champions. However, their immense gravity affects the objects around them, allowing us to detect their presence indirectly. This gravitational influence can be observed in the way stars and other celestial bodies behave in the vicinity of a black hole. It's like watching the ripples in a pond to understand that a stone has been thrown in, even if you can't see the stone itself. One way is by observing the motion of stars orbiting a black hole. These stars move in peculiar ways, often at incredibly high speeds, due to the black hole's gravitational pull. By tracking their orbits, scientists can map out the invisible gravitational landscape sculpted by the black hole. Just like planets orbit stars, stars orbit black holes. The difference is that the gravitational force exerted by a black hole is far more intense, causing the stars to move in ways that would be impossible if they were orbiting a regular star. This dance of the stars around an unseen partner provides crucial clues about the black hole's presence and properties. By carefully measuring the speed and trajectory of these stars, astronomers can infer the presence and mass of an unseen black hole. This requires precise observations and sophisticated calculations, often involving years of data collection and analysis. The results, however, can reveal the hidden giants lurking in the depths of space. Another method is by observing the radiation emitted by matter falling into a black hole. As gas and dust are drawn towards the black hole, they accelerate and heat up, emitting various forms of radiation, including X-rays. This process, known as accretion, can produce some of the brightest sources of radiation in the universe. As gas and dust spiral towards a black hole, they heat up to extremely high temperatures and emit X-rays. These X-rays can be detected by space telescopes, revealing the location of the black hole. The intense radiation provides a beacon, signaling the presence of a black hole, even though the black hole itself remains invisible. These X-rays can be detected by space telescopes, revealing the location of the black hole. Instruments like the Chandra X-ray Observatory and the XMM Newton telescope are specifically designed to capture these high-energy emissions, allowing astronomers to pinpoint the exact location of black holes and study their properties in detail. Scientists also use a technique called gravitational lensing to detect black holes. This phenomenon occurs when a massive object, like a black hole, bends the path of light passing by it. The gravitational field of the black hole acts like a lens, magnifying and distorting the light from objects behind it. Massive objects like black holes bend the path of light passing by them. This bending of light can create multiple images of the same object, or stretch and smear the light into arcs and rings known as Einstein rings. These visual distortions are telltale signs of a black hole's presence. This bending of light can magnify and distort the images of distant objects, creating a gravitational lens. By studying these distorted images, astronomers can not only detect black holes but also measure their mass and other properties. Gravitational lensing provides a powerful tool for exploring the invisible universe. By observing these distorted images, astronomers can infer the presence of a black hole. Each method, whether it's tracking star movements, detecting X-rays, or observing gravitational lensing, adds a piece to the puzzle, helping us understand these mysterious and fascinating objects that shape our universe. A universe of black holes. Exploring different types. Black holes come in a variety of sizes, each with its own unique characteristics and formation process, making them fascinating objects of study. Stellar mass black holes, the most common type, form when massive stars collapse at the end of their lives, creating a powerful gravitational pull. These black holes are typically 3 to 10 times the mass of our Sun, but squeezed into a city-sized region, making them incredibly dense. Supermassive black holes, on the other hand, are millions or even billions of times more massive than our Sun, dominating their surroundings. They reside at the centers of most galaxies, including our own Milky Way, influencing the motion of stars and gas. The formation process of these behemoths is not fully understood, but they are thought to have played a crucial role in the evolution of galaxies over billions of years. Miniature black holes, also known as primordial black holes, are hypothetical objects that are much smaller than stellar mass black holes, yet equally intriguing. Some theories suggest that these tiny black holes could have formed in the very early universe, shortly after the Big Bang, during the universe's infancy. However, no definitive evidence for their existence has been found, leaving their reality a tantalizing mystery for scientists. Journey to the singularity. What lies within the abyss? At the center of a black hole lies the singularity, a point of infinite density where the laws of physics break down. This singularity is a region where the gravitational forces are so intense that they warp space and time to an extreme degree. The concept of a singularity challenges our understanding of the universe, as it represents a place where the known laws of physics cease to apply. As matter falls into a black hole, it gets compressed into an infinitely small point, creating a region of unimaginable density and gravitational force. This process is known as accretion, where the matter forms an accretion disk around the black hole before being pulled into the singularity. The intense gravitational pull of the black hole accelerates the matter to incredible speeds, heating it up and causing it to emit powerful radiation. The singularity is often described as a tear in the fabric of space-time, a place where our current understanding of physics collapses. This tear creates a boundary known as the event horizon, beyond which nothing can escape the black hole's gravitational pull. The event horizon marks the point of no return, where the escape velocity exceeds the speed of light. As an object approaches a black hole, it experiences spaghettification. This phenomenon occurs because the gravitational forces acting on the object are not uniform. The side of the object closer to the black hole experiences a much stronger gravitational pull than the side farther away. This is a process where the tidal forces caused by the black hole's intense gravity stretch the object into a long, thin strand resembling a spaghetti noodle. The difference in gravitational pull across the object creates extreme tidal forces that elongate and compress it. This happens because the gravitational pull on the part of the object closer to the black hole is much stronger than the pull on the part farther away. The result is a stretching effect that can tear apart even the most robust materials. What happens inside a black hole remains one of the biggest mysteries in astrophysics. The conditions within a black hole are so extreme that they challenge our current understanding of the universe. Scientists continue to study black holes to uncover the secrets they hold. Our current understanding of physics cannot fully describe the conditions at the singularity. The singularity represents a point where the known laws of physics break down, and new theories are needed to explain the phenomena that occur there. Some theories suggest that black holes could be gateways to other universes or dimensions, but these ideas are still highly speculative. The concept of black holes as portals to other realms is a fascinating area of research that continues to captivate scientists and the public alike. While we may not yet fully understand the true nature of black holes, they remain one of the most intriguing and mysterious objects in the universe.